In this video, I will introduce a new model called a polyconix, and there are 5 unique harmonic notes that model the geometric properties of the polyconix. The conics on its surface represent abutting cones within the sphere itself, and the polyconix have similar properties to the 5 platonic solids. There is a icosaconix consisting of 20 cones. There's a dodecaconix, which is an arrangement of 12 cones. The octaconix is an arrangement of 8 cones. The hexaconix is an arrangement of 6 cones. And the tetraconix is an arrangement of 4 cones. So let me use the dodecaconix as an example to demonstrate how to derive its geometric properties, and then show how to construct the conical sections that will be required. This is one of the 5V notes, known as the 5V upper 3E that we saw earlier. And this note is a geometric model for the actual dodecaconix as seen here. And this is an arrangement of 12 cones. Now the actual cone itself has a planar radius of RP. That's the same as the conix on the note itself. Now at this point, even though we can construct this harmonic note, we actually don't know what the conical radius is, because we've just set the compass to connect between the vertices and an edge. This is probably going to see more clearly here on a dodecadecic that we saw earlier, and these circles would be embedded inside this pentagon, and you can see that the conical radius is between the face of the dodecahedron and an edge. We do know the spherical angles for this pentagon. We'll be using that and the law of cosines to derive the actual subtended angles inside, so we can get the aperture of this cone. It's going to help us to do further calculations. Now, in addition to, once we have the aperture of the cone, we can compute the planar radius of the cone, and more importantly, we can calculate the circumference of the cone. And then we can basically start with a circular plane, the radius r, that of the sphere itself, and cut a wedge out of the circle, and that can maybe be sort of pinched and create the cone we want to have a particular aperture for a particular polyconix. And I'll go into more detail in the following slides to do that. This diagram illustrates the geometric model that shows the geometric properties of the conix, which we had seen earlier. I have added the subtending angle to the model that represents the aperture of the conic section of the polyconix. This diagram shows the simple sine relationship between the cone aperture and the base circle of the cone, which has a planar radius of RP. This diagram shows a conical wedge that is used to construct the cones, where the conical wedge angle is a fraction of the circle, which is a ratio of the planar radius to the spherical radius, or sine theta times 360 for a unit sphere. We cut out the leftover pi section of the circle, and we can then form the cone by pinching the conical wedge together, where the cone will now have the desired aperture for this polyconix. So the other characteristic of each of these polyconix, here's a tetraconix, is that the cone abuts 3 other cones. So we need to identify those 3 abutment points. For the hexaconix, each cone is abutted by 4 other conics. So we've got these 4 abutment points to define. And for the octaconix, Each cone abuts 3 other cones. Here again we've got 3 intersection points to identify. For the Dodecaconix, each cone is surrounded by 5 other cones. So we've got these 5 abutment points to identify. And then for the Octaconix, each cone has 3 abutting cones, and we'll identify those as well. Let me show you how we can easily derive the subtended angles for each of the cones of these polyconics by using the polydesic models we explored earlier, for which we've already calculated the subtended angles for each of these edges. So this is an overlay between a icosahedesic and a dodecadesic, and we know these edge lengths already. The edges intersect, or perpendicular, and divide each of its edges into 2 halves. Well, each of these halves are actually the subtended angles we were going to need for each cone, and let me demonstrate. So if we place the compass at the face of a dodecahedron, you see it intersects with the edge, and that's the circle of the conics we need. So this half edge of the icosahedesic is what we need, as well for conics centered at the face of the icosahedron. That's the circle we need for the base circle of the conics. I will use this diagram to illustrate the subtended angle of the icosahedesic. The diagram consists of an overlay of 2 structures seen earlier, the icosahedesic and the dodecadesic, for which we already have derived their subtended angles. It turns out that the subtended angle of the icosahedesic is 1/2 of the subtended angle of the dodecadesic, as seen here. The nomenclature used here is as follows. The subtended angle theta of the icosahedesic is a property of the harmonic note 5F upper 2E. Now we will calculate the conical wedge CW of the icosahedesic. Its subtended angle is 1/2 of the edge arc of the dodecadesic that I have pulled from an earlier calculation. That results in an angle of 20.905 degrees. We then take the sine of this angle and multiply it by 360 degrees. This results in a CW of 128.456 degrees. We divide this by 3 to find the abutment points. And this is the resulting template for the conical wedge of the icosahedesic, and I will demonstrate its construction. Now I can show you how to construct the icosahedesic from the template we just defined with this conical wedge. This can be sort of pinched into this conical shape. We've got the 3 abutment points identified, and then 20 of these cones can be arranged into the actual icosahedesic itself. Now conversely, the subtended angle of the dodecaconix is 1/2 of the subtended angle of the icosahedesic, as illustrated here. And the nomenclature used here is as follows. The subtended angle theta of the dodecaconix is a property of the harmonic note 5E upper 3E. Now we will calculate the conical wedge CW of the dodecaconix, where its subtended angle is 1/2 of the edge arc of the icosahedesic that I have pulled from an earlier calculation, and that results in an angle of 31.7175 degrees. We take the sine of this angle and multiply it by 360 degrees. This results in a conical wedge of 189.263 degrees. We divide this by 5 to find the abutment points, and this is the resulting template for the conical wedge of the dodecaconix, and I will demonstrate its construction now. Now I'll show you how to construct the Dodecaconix from the template we just defined. It's got its 5 abutment points marked on here, and this can be twisted and pinched into this conical shape. We can take 12 of these cones and be assembled to create the actual dodecaconix itself. I'll use this diagram to illustrate the subtended angle of the octaconix. The diagram consists of an overlay of 2 structures seen earlier, the octadecic and hexadecic, for which we've already derived their subtended angles. It turns out that the subtended angle of the octaconix is 1/2 of the subtended angle of the hexadecic, as seen here. The nomenclature used here is as follows. It's a subtended angle theta of the octaconix is a property of the harmonic note 4F upper 2E. Now we'll calculate the conical wedge CW of the octaconix. Its subtended angle is 1/2 of the edge arc of the hexadecic that I have pulled from an earlier calculation. This results in an angle of 35.264 degrees. We take the sine of this angle and multiply it by 360 degrees. This results in a conical wedge of 207.846 degrees. We divide this by 3 to find the abutment points, and this is the resulting template for the conical wedge of the octaconix, and I will demonstrate its construction. So now I can show you how to construct the octaconix from the template we just defined with the defined conical wedge. This can be pinched into a cone shape with the 3 abutment points defined as required, and 8 of these cones can be arranged and assembled into the octaconix as seen here. Going back to the diagrams, conversely, the subtended angle of the hexaconix is 1/2 of the subtended angle of the octadecic, as illustrated here. And the nomenclature used here is as follows. The subtended angle theta of the hexaconix is a property of the harmonic note 4V upper 2E. Now we will calculate the conical wedge CW of the hexaconix, where its subtended angle is 1/2 of the edge arc of the octadecic that I've pulled from an earlier calculation, and this results in an angle of 45 degrees. We take the sine of this angle and multiply it by 360 degrees. This results in a conical wedge of 254.56 degrees. We then divide this by 4 to find the abutment points, and this is the resulting template for the conical wedge of the hexaconix, and now I can demonstrate its construction. And now I'll show you how to construct the hexaconix from the template that we just defined. Again, this can be pinched into this cone shape with the 4 abutment points defined, so we can assemble 6 of these cones to create the actual hexaconix itself. I will use this diagram to illustrate the subtended angle of the tetraconix. The diagram consists of an overlay of the tetradecic and a dual tetradecic, for which we already derived the subtended angle for. It turns out that the subtended angle of the tetraconix is 1/2 of the subtended angle of the tetradecic, as seen here. The nomenclature used here is as follows. The subtended angle theta of the tetraconix is a property of the harmonic note 3V upper 2E. Now we will calculate the conical wedge CW of the tetraconix, where its subtended angle is 1/2 of the edge arc of the tetradesic that I have pulled from that earlier calculation, and that results in an angle of 54.7356 degrees. We then take the sine of this angle and multiply it by 360 degrees. This results in a conical wedge of 293.939 degrees. We divide this by 3 to find the abutment points, and this is the resulting template for the conical wedge of the Tetraconix. And now I'll demonstrate its construction. And now I'll show you how to construct the Tetraconix from the template we just defined, with the defined conical wedge. This can be again pinched into this cone-shaped design with the 3 abutment points marked off. And 4 of these cones can be assembled to create the Tetraconix itself.